Hi students, hope you are all doing fine and welcome to Optimization Tutorial 25. Today we are going to discuss one more method for calculating the gradient vector, and this has become quite pervasive in recent years because it is included in one of the Python libraries and it is known as automatic differentiation. We will actually use AD for this particular method, and today we are going to discuss how to use this method in optimization. I'm Dr. Ganguly. Now in today's tutorial you are going to learn about how to use this method to differentiate a function, and essentially what this method tries to do is that it takes a piece of code which has been written for a function calculation of the function f of x, and then it essentially differentiates it using computer mathematics and so on. Now we are going to show this for a single variable function, then we are going to do this for a gradient vector. We are going to use the method for the BFGS method, which is the optimization method for unconstrained problems given by this set of equations here. We are also then going to use the BFGS method and the Booth function, which is a test function, to check out this AD method. Now, of course, you remember the BFGS method has the form xk plus 1 is xk plus alpha k dk, where dk is obtained by solving the system. bk dk is minus ck. C is the gradient vector. B is the matrix which is built up by the BFGS method, and D is the search direction. Also, alpha k is the step size and x is the current vector of design variable. Xk plus 1 is the next vector of the design variable. So of course, in optimization, one of the most important things is how do you calculate the gradient vector. And in previous lectures, we have discussed various methods out there. One of them, of course, is differentiation. If you are able to differentiate a function, good for you. But if you are not, there are also methods involving numerical derivatives such as finite difference, and also the complex step method, which we have discussed in lecture 24 and tutorial 24. Now, if you want to look at the theory of this method, you can take a look at optimization lecture 25 for a detailed description of AD. And in today's tutorial, we are going to use Python code and the JAX library. This JAX library is very powerful. I think it was developed by Google and some more people, and it's often used in machine learning. So machine learning, of course, requires gradients all the time. Remember, gradient search is an integral part of machine learning. So let's straight away get into coding, and let's write a Python program to calculate a derivative of this function using AD. Now this function is a simple single variable function, so x to the power 5 plus 2x cubed minus 3x squared minus sin x minus e to the power x. And of course, this is something which we can easily differentiate from our knowledge of calculus at high school level. So we will do that, and then we will compare it with the value which comes out of the AD method. We are going to do all this at the point x is 1. So if we take the function here, the function f of x, we can immediately write the Python function corresponding to this math function, and we can put in here x to the power 5 plus 2x cubed minus 3x squared minus sin x minus e to the power x. Now we are going to use a certain variant of the NumPy library which uses JAX, so I will put this J and P in place of NP at all places. I'm going to explain that to you in the next slide in the main program. Now for this function, because it's so simple, I can differentiate it by my knowledge of calculus, and so I get f dash x is 5x4 plus 6x squared minus 6x minus cos x minus e to the power x. And I have coded in this also here. So this serves as a benchmark by which I can compare whatever I am getting out of the AD process. Now this is the main code which essentially is going to invoke the function which we are going to use. So we first have to import JAX, and then we have to import jax.numpy as JNP. Now at this point, this particular line of code is extremely important. So JAX has this built-in function called grad. So I can define, for example, the derivative as jax.grad and f here. F is the function, remember that we put in the function in the previous slide. Now I define the point x0 is 1, which is the math here, and then I print out f of x. So I put f x0, then I print out the value coming out of AD, and this JAX.grad is essentially going to use AD, and it's going to give me the derivative at x0, and I'm also going to print out the exact value from the closed form solution which I defined in the program before. So I'm going to call that dfx and exact here, and then when I print these out, you can clearly see that the AD value exactly matches with the exact solution. So this is the very powerful tool which you can use in Python. JAX, remember that if you are more interested, just search Google for JAX and you will find a plethora of documentation out there for the JAX library. So this not only works for scalars like I showed you now, but it also works for vectors. So that's what we will discuss next. So let's now look at the function, which is a two variable function. So it's going to require us to use vectors. And now we have to use the method to find the gradient vector for this function at the point 5 minus 5. So let's try to do that. Now once again I define the function f of x, and I define the gradient here by differentiation. So you can clearly see the function is simply x1 square plus 2x2 square plus e to the power minus x1 minus x2, which I have defined here as term. So essentially you are seeing here I have split the function into two parts. I have this part here, I have put it in here. And again, remember, because I'm using JAX, I need to use J and P here. Now, as far as the gradient is concerned, I return this two-dimensional vector. This vector is the Pythonic representation of this math given here in the red equation. So C is the gradient vector. And again, I have coded that in here. So you have 2x1 minus e to the power minus x1 minus x2, and I have 4x2 minus e to the power minus x1 minus x2. Of course, remember Python uses Python uses x0 and x1, and math uses x1 and x2. So that's the mental change you have to always keep making between math and Python. So now let's write the main program. Once again, we import JAX, we import jax.numpy as j and p, and then we straight away invoke the grad method in JAX, and we define this thing called ad slash grad f, which we put whatever is coming in jax.grad f into this particular variable. And then what I do is I define x0 as a vector of two dimensions. So this is 5 and minus 5. And then I print the function value at x0. I print the differentiated value coming out of the grad f here. And then I also print out the exact gradient vector, which I know from hand calculations, which I coded into the previous slide. Now I immediately get the output here, and you can see exact match between the value of the derivative coming from the AD method and the exact value. So now you see how you can use this method in the multidimensional functions. Once you know about two dimensions, you can essentially extrapolate this to n dimension, because we have moved from scalar to vector space. Now that we can calculate the gradient vector, let us use the AD method and the BFGS function to find the minimum of this function here. And we are going to start with the point 5 minus 5. Now this function, let us look at it mathematically. So I can take this function, I can differentiate it, I can set that gradient vector to 0, and I immediately get the solution x1, x2 is 0. So that's the optimal solution for this problem. And this function has a Hessian value given by e pi 7. So you can see by differentiating the gradient vector twice with respect to x1 and x2, you are going to very easily obtain the Hessian matrix here. Now the reason I created this function is that I would like to see the H matrix come out in this form, because then I clearly know these numbers and I can check it out very quickly. So remember, the minimum point here is simply 0, 0. That's the stationary point of this function. And what I'm going to do is I'm also going to try to print out the B matrix at the end and see whether it's positive definite or not. So that's going to confirm if this is a minimum point or not. Let's code in the function and the gradient. So I have coded in here. Remember, I'm not going to use the grad f here for performing the BFGS. I'm only going to use it to check the gradient which is coming out of the AD method. So again, as far as numpy is concerned, it's got some built-in variables like e, pi, and so does jnp here. So I have replaced the np by jnp, and so you can see this is the function and this is the gradient vector. Now the H matrix is given by E pi pi 7. Again, I code it in here. I'm not going to use the H matrix anywhere, but I'm going to print it out so that I can compare it with the B matrix predicted by the BFGS method at the end of the program. I'm also going to require a simple function for the one-dimensional search, and this function returns the value of f at xk plus 1, that is f at x plus alpha into d. For the one-dimensional search, I use a very simple method. I take the value of alpha, I go from delta, 2 delta, 3 delta, all the way forward, and then I bracket the minimum between some q minus 1 delta, q delta, and q plus 1 delta. And then once I have bracketed the minimum, I can get the minimum point as the midpoint of the lower bound and the upper bound of this value. And what I do is I keep reducing this delta. So I start with some delta is 0.05, then I make it delta is delta by 10, and I keep doing it till I converge as far as the one-dimensional search value alpha star is concerned. And also the BFGS formula, with which you should be familiar by now, essentially starts with B0 is I, and then it updates the B matrix using this formula here, that is bk plus 1 is bk plus this matrix plus this matrix, and these two matrices are obtained by using these vectors sk and yk. So yk is the difference between the gradient vectors at point k and k plus 1, and sk is the difference between the design vectors at point k plus 1 and k. So once I have these two, I can very easily craft the BFGS method. Again, details about the BFGS method are given in lecture 23 and tutorial 23. You can check it out if you want. Let's put in the BFGS function, and we have seen this function before in case you have gone through those methods in the past. I start with B0 is I, you can see here, so I have to basically invoke this function BFGS in the main program. It takes in a starting value x0, some tolerance numbers which are small numbers to manage convergence, and max is what I use in the for loop here. And then what I do is that I usually build up the vectors. For example, I build up sk and yk, and then what I do is I use this formula for b here, and then I solve the linear system bd is minus c in this here. Now the main difference you will see here compared to the previous program is that I am using this AD graph grad f for calculating the gradient vector, and I'm printing out this also. And the next thing I'm doing is I am also printing out the exact gradient vector. So this is going to let me calculate the exact gradient vector and compare it with the one I have obtained through the AD method. But remember, what I'm using here in the code is this C value, and this C value is coming from AD method here. Finally, I'm going to print out some of these values at convergence. I'm going to print out the converged x value, which should hopefully be 0. I'm also going to print out the value as far as the B and the H matrix are concerned, and I'm also going to print out the eigenvalues for the B and H matrix, and that should tell me whether these are positive definite at the minimum. They should be, and in that case I know it's a minimum point. Let's write the main program. So again, I import JAX, I import jax.numpy as jnp, I define these tolerance and max values, and then I invoke the jax.grad function on the function f. I use the starting point 5 and minus 5, which is x0 here, and then I invoke the BFGS function at x0 tol 1d max. Tol 1d is actually used in the one-dimensional search. So this is the numerical result for the BFGS. You can see this here. So you have the x0 at 5 minus 5, you have b0 is I, and then you see rapid convergence. Interesting thing here is that the gradient vector as predicted from the exact value which I have coded in is identical to whatever I am getting from AD. So this shows us how good the automatic differentiation is in getting the values here, and it converges very quickly to 0 0, and you can also see that the B matrix matches the H matrix here. And of course, as far as the matrices B and H are concerned, these are positive definite because the eigenvalues come out to be positive in both these cases. Let's try a different function here. Let's try the booth function. So this is a test function which is sometimes used in optimization. And again, I'm going to use AD here with BFGS to minimize the booth function. And the booth function here is given in this form. Very often the test functions are given in the form xy rather than x1, x2. And so you can make that transition to Python mentally. I'm going to start from the point 0 0, and in this case the optimal point is known as 1 3. We are not going to differentiate this function at all here. We are simply going to use AD to solve this problem. So this is the booth function, and I have coded this function in here. Very simple function to code in. So remember, x is x0 and y is x1 here. Again, x is x0 and y is x1 here. So once again, I use the BFGS function. Some small changes here. I have stopped printing out that comparison with the exact solution and the AD. I am simply going to use the AD solution right here. And then I'm going to build up all the things in the BFGS method. And when I have converged, I'm going to print out only the B matrix and the eigenvalues corresponding to the B matrix, because I have not bothered now to actually mathematically calculate the gradient vector or the Hessian matrix here. I am simply using the AD feature from JAX. So let's check out the main program once again. Small changes I have made here and there. One of the things I did is I reduced tall 1D to 0.01 and max also, because this was taking a lot of time. And once I did that, my code converged very rapidly. So let's see how it goes. So you can see here the convergence is pretty rapid, and I start from 0 0, and I have quickly converged to the point 1 and 3. So very interesting here. You see we did not have to differentiate the function at all in this problem. So this is something which you often do using code nowadays, is that you can invoke something like the JAX library, and then you can get your differentiation done by very simple means by the computer itself. You do not have to bother about differentiating and creating that function. Of course, if you are able to do that, it can give you high-speed convergence, but in many situations, particularly in machine learning, you do not have the function in a form which is easy to differentiate. You have it in the form of some computer program or some data itself. So that's where it's coming in handy. Now, one of the things I like about the BFGS method is that it gives you the B matrix at the end, which is something which should be very close to the Hessian matrix. And therefore, if you were to check out the positive definiteness of the B matrix, it should be positive definite at convergence. And if it is, then you know this is a minimum point. Remember the optimality criteria, that if the Hessian matrix is positive definite, you have a minimum point. So I'll leave you with this problem for homework. So we have done this particular problem for a 2-dimensional case. So extend it to a 3-dimensional case where you can use this function here, which we have used several times before. So now you have x1, x2, and x3. So you have 3 design variables. You can start from this point here. And again, this will give you a good feel about how to use the JAX library and how to use optimization in conjunction with the AD method. Now, do remember, you can do this in Google Colab, you can do this in Jupyter Notebook, and in any other place. So again, it's important to use some of these tools here, but again, there are positive aspects and there are some negative aspects also. So as far as this particular approach AD is concerned, it essentially uses computerized differentiation. And one of the biggest advantages, you do not need to calculate the step size h. If you recall with our experiments on numerical differentiation, calculating the appropriate step size is a big problem whenever you use forward difference, backward difference, or central difference formula. To some extent, this is mitigated when you use the complex step derivative. Now, one of the advantages of AD is that the derivatives are extremely good. And one of the negative aspects is that it can be somewhat slow because after all the computer is doing the task of differentiating here. So what it does is it takes your function subprogram and it essentially creates a program which is a derivative program of this particular program. So it really does all these things behind the scene and you do not have to think too much about it. But there are a lot of resources on AD. You can look at the lecture 25 which I have created to get some concept about how this method works, and also make it a point to look at lecture 24 on numerical differentiation, because you need to know all these methods to figure out which method is best for you. Nowadays that the complex step derivative is there, that can give good competition as far as the AD is concerned. So you may think about using the complex step in some cases, but in some cases you may be better off by using the AD method itself. Now, one of the important things here is that you can use the JAX library. And again, remember jax.numpy as JNP has to be put in various places. And the important function to keep in mind is jax.grad. And f here is the function which you are calculating. So you need to write a function subprogram in the form f of x, and then you can invoke jax.grad to get your gradient vector. So we will end this lecture today, and now you have a bag of tools as far as differentiation is concerned. Remember, differentiation is something which is extremely important, not only in optimization, but in machine learning. So in fact, you can think of all the problems around the world as essentially minimization problems. You could pose them as some kind of minimization or maximization problem. Maximization can of course be converted to minimization problem very simply by simply multiplying by a negative sign. So a large number of problems out there, not only in science and engineering, but in business, in all fields, in social sciences, can be solved by using optimization and machine learning. So that's going to greatly help you if you know how to calculate derivatives well, because at the end of the day, mostly gradient based optimization methods are being used as far as minimization is concerned.